we've got some alternate activations. Ooh, this could get really dicey fast. Battery power, that is. Alternate activation. So we went through and said we could add strong acids to protonate our alcohol to make it a good leaving group. Okay, the issue with that is that most of those reactions went under the unimolecular fashion, okay, because we're in a protic environment. Those unimolecular systems get us two products, okay, which is why when we looked at that spider diagram, let's see, how far back is it? Yeah, shouldn't have done that. Holy crap, where is it? There it is. When we looked at that, notice, do we see any stereochemistry specified? No. At best, we see the trans double bond. Why would we expect the trans and not the cis?
It's concentrated acid.
Concentrated acid should still get a double bond. Why would I get trans and not cis?
More stable.
It's more stable. In the process of doing that mechanism, it's going to try and generate the most stable double bond possible, unless something prevents it. So for the most part, we'll get the trans. Okay? If we continue back through Jiminy Christmas, we take a look at this slide. What is different about this slide? Stereochemistry out the yin-yang. And that's because the stereochemistry is really important. The stereochemistry is now specific to these reagents. These become much more useful reagents because I get one product. Okay? That's why we would tend to stick with these. So if you're seeing stereochemistry in a substitution, you should be thinking these reagents. Okay? Do you notice anything kind of bizarre with any of those? What's that? Okay. P what R? P what R? PX, what is the X standing for?
Halide?
Yeah, pretty much any halide. The typical ones you'll see would be PBr3. Whoop, that's an eraser. PBr3 or PCl3. Both of them are doing the same thing. Okay? They're running that same mechanism where the X is either going to be bromine or chlorine. Okay? Anything else that you notice that's kind of interesting on that? Oh, I completely agree. It's a bit weird that I see SOCl2 show up twice. Okay, well, I must just have repeated that. I only have to memorize one of those. What's the difference? The stereochemistry is all of a sudden switched. In one case, I had the exact same stereochemistry as the starting alcohol. In the other case, it inverted. Why? In one case, I add PYR, which is an abbreviation for pyridine. Pretty darn close. Pyridine. Pyridine changes the dynamics of that mechanism, and we can end up getting an inversion in stereochemistry. So we have to be very careful when we see SOCl2 to see what else it's in the presence of. If it's in the presence of pyridine, we see an inversion in the stereochemistry. Without the pyridine, we get retention. Okay. Why might retention be weird? What does retention mean? The leaving group left and the nucleophile came in. Where did the nucleophile come in? If it came in from the backside, I would get inversion in stereochemistry. It had to come in from the same side. But what does the nucleophile or leaving group leave with? Electrons. And what does the nucleophile supply? Electrons. Would we expect to ever get retention? No. Something weird is going on within that mechanism. There are cases that we've seen where we get retention. The BH3 reagent gave us retention. It was that syn addition of the hydrogen and the boron. It had to do with very quick chemistry all happening in one centralized location. Somehow or another, SOCl2 will allow for that as long as pyridine is not present. Make sense? Okay. So let's go ahead and take a look at SOCl2. It's our sulfoxide-activation. Thionyl chloride is the name for it. It is an awful, awful smelling compound. It reacts insanely quickly with water in the atmosphere to form sulfur dioxide. That rotten egg smell, if you've ever smelled rotten eggs, is sulfur dioxide. Okay? This is now concentrated sulfur dioxide. It reeks horribly. Okay? But depending on our conditions, we can get some kind of interesting chemistry coming out of it. Okay? So let's take a look at what we would predict. If we got thionyl chloride shown and we have our alcohol, what would you predict to be the chemistry? How is this going to start? Again, we have a hint at the top. It says sulfoxide-activation. What electron pairs?
On the oxygen, on the substrate, not the other one.
Okay. Lone pairs on our alcohol will attack.
Sulfur,
Why would they attack the sulfur?
because then the pi bond electrons can go to oxygen.
Why would those pi electrons be moving towards oxygen?
That's one possibility.
Oxygen is more electronegative than sulfur. That's what's happening. Chlorines, also exceptionally electronegative. Every atom attached to that sulfur is pulling electrons away from the sulfur. That sulfur is insanely positive, right? Really willing to accept electrons. Okay? If we looked at the result of that, simple arrow pushing, we would have something along these lines. Negative charge, chloride, hydrogen, positive, right? Okay. Does our oxygen want to be positive? No. So it's itching to get electrons from somewhere. Where could it get them from? Could steal them from the hydrogen. That's a possibility. Where else could it get them from?
The carbon?
Could get them from the carbon. That's a possibility.
Just reverse.
Could just reverse. I don't even want to draw that one, but yes, it could reverse. So we've evaluated what could happen around the positive oxygen. Is there anything else that could happen or anything else reactive in that structure? A negative oxygen. Where could those electrons go? To the what? There's no resonance. I heard something about going to the positive. Can it do that? How do electrons move? Bond to bond, but our electrons aren't starting on a bond, so I don't accept that. They can move from atom to... Nope. We cannot move electrons from atom to atom. That is not existence. Atom to bond. Okay. The atom-to-atom connection, if you wanted to even attempt to do that, would be forming a three-membered ring as a transition state. Oxygen, sulfur, oxygen are three. That suggestion, not a good one. Okay, or not a useful one. So what else could we do with that negative? Okay, we got to move them someplace. We said if we got electrons on an atom, we only have one place to move them, which is where? To a bond. If I move those electrons down, well, now what happens?
So you just reverse the reaction. Exceeded octet.
The sulfur exceeds its octet. Sam is saying we reverse the reaction. So what Sam sees is as soon as that happens, well, then the oxygen gets kicked back out. Is there another leaving group? The chloride could leave. Okay. As long as we are in this system, pretty much all of these things happen relatively close to simultaneously. Okay. First and foremost, we will kill that hydrogen. Okay. What does that then do for us? Whoops. That fixes the positive charge on that oxygen. I still have the negative charge on the other one. Those electrons can come back down kicking out the chloride. Okay? What can you tell me about the sulfur? How many electronegative atoms are connected to it? There's still 4. Okay? So it's very, very positive. So what does it want? Electrons. So it started to withdraw some electrons from that first oxygen. Okay? And then it gave up some electrons with that chloride. Is there another source of electrons? The oxygen can steal electrons from the carbon, forming our leaving group. Now our sulfur picks up those electrons. Okay? The chloride, seeing a positive charge, immediately jumps in on that positive charge, maintaining the stereocenter, because it's happening all at once. That will also click out our other chloride. The end result, if we step through this slowly enough, ignore the pyridine for the moment, would be our chlorine attached to our structure and SO2 as a product. What do we know about SO2 other than it stinks to high heaven? Why does it stink?
The gas.
It's a gas. The gas can leave the system, preventing the reverse reaction, because I now don't have the reagents to reverse the reaction. It's left. Okay? So this strongly favors product formation. Okay? So SO2, the formation of that, really, really helps out. A question comes up about the stereochemistry. Without pyridine, this all happens almost instantaneously, dropping the chlorine in the exact same spot. With pyridine, what changes? Well, what does pyridine have? Electrons. With those electrons, what could it do? Could share them with sulfur, kicking out our chloride. We then make a very, very large leaving group. If the leaving group is very large, can the chloride come in and immediately attack? No. Which means the chloride is then forced to attack from the backside, and I get the inversion of the stereochemistry. Okay? So depending on our conditions, we get an inversion of stereochemistry or not. Some of the cool chemistry. Anything with an OH, thionyl chloride reacts with. That's because thionyl chloride is that insanely reactive. All right, so well, that's just alcohols, right? Only alcohols have OHs. No, what else has OHs? Carboxylic acids. So if I have a carboxylic acid and I don't want that acid functionality anymore, I can add thionyl chloride, I get rid of the OH, and I replace it with a chlorine. Okay? Super relevant for our third unit. Okay? The secondary chemistry that's really neat is that if we don't have pyridine, the chloride immediately substitutes back in, getting retention in stereochemistry. So pyridine forces a backside attack. Without pyridine, we get retention in stereochemistry. Okay. Super subtle nuance of that reaction. It's something to at least be aware of when you go through and do that chemistry. Okay. Questions about that? So all the sterics and stereochemistry that we talked about in first semester still holds true. Those still apply how our reaction works. The biggest thing that you need to know is what we started with. What are the reagents and what it does? Okay? So I actually just talked about this. Pyridine is typically seen as just a solvent, but those lone pair electrons can coordinate to the sulfur, making that a very large leaving group. That very large leaving group sterically blocks the chloride from interacting immediately, and it has to do a backside attack. That's why we get the inversion. Okay? I do want to call your attention to this thing at the bottom here. I've seen questions go both ways. Okay? Saying just thionyl chloride, what happens? Oh, you get inversion of stereochemistry. Okay? Thionyl chloride on its own does not get inversion of stereochemistry. Thionyl chloride with pyridine gets inversion of stereochemistry. But I've seen questions get formatted where they aren't being specific in that nuance with the solvent. Which means on any test that I write, you can feel free to call me out on it and be like, no, you made a typo there. That's cool. Do it. Okay? On the ACS, I watch that test like a hawk for things like this. Okay? And if it does it, I will grade accordingly for both. Okay? Make sense? Okay, so retention of stereochemistry means no pyridine. With pyridine, we get inversion. How about our phosphorus activation? Okay, well, when you look at this reagent, what do you now see? Or this sequence, what do we have? As a hint, kind of similar to what we did in the last one. I also tried to be a little bit annoying with it too, believe it or not. So the first thing, the whole point of this is to make the alcohol a better leaving group. So we're taking advantage of the lone pair electrons on that oxygen, which means our oxygen is acting as a partial negative. For it to react, what does it need to react with? A partial positive, an electrophile. So that means the other structure must be acting as an electrophile. Bromine, tons of electrons. When it's attached to another bromine, we have an electrophile. It's not attached to another bromine. So that doesn't quite lead us to believe the bromine. So maybe it's the phosphorus. Why might we be hesitant to say the phosphorus is an electrophile? It has the lone pairs. I intentionally drew those on there because they are there. Okay? Why will the phosphorus still act as an electrophile?
It's connected to 3 electronegative.
Those 3 electronegative bromines are all pulling electron density away from that phosphorus. The phosphorus does act as a partial positive. The electrons come out, attack. I probably shouldn't have it attacking the electrons. Let's at least make it look like it's attacking the phosphorus, kicking out our leaving group of a bromide. Okay. We had this same issue with sulfur. Okay. After that, what can happen? Well, now I have a pretty good leaving group again. The oxygen doesn't want to be positive. What else is chilling in solution right now? Rhymes with chloride. We have bromide floating around in solution. The bromide can now do a backside attack and kick out our leaving group. And we get our inversion in stereochemistry. Okay. The other product of this is that phosphorus oxide compound. That compound is more stable than with the bromines. We don't get a gas, but it then kind of separates itself from the system. What type of reaction did we do? So in that question, it's a bit difficult. We could be looking at this reaction, beginning to end. What type of reaction did we do? Substitution. How about this reaction? What did we do? Okay, that's a little bit weird, right? Why would it be weird to call that an addition? There's no pi bond. Okay, we are still effectively losing electrons. The lone pair is what's getting added to instead of a pi bond. Okay, so we are running kind of an addition there. We still have 2 pieces becoming 1. The last one. It's a substitution. Okay. So looking at those pieces, we can kind of put it together and figure it out. Mechanism. Okay? When we're being concerned about the mechanism, we're asking really for that overall thing. Uh-oh. Reconnect. We're asking for the whole shebang. Okay? We're asking kind of what happened as a first approximation for that mechanism. Okay? This is where it gets weird because the mechanism is officially an addition followed by a substitution. Okay? But beginning to end, that substitution reaction looks most like what mechanism? It is substitution, but which one? SN1 or SN2? SN2. We're primarily concerned about that backside attack. Okay? So we're running an SN2 reaction in this case. Right? We get the backside attack, we get the inversion in stereochemistry, and all that fun stuff that goes with it. Make sense?
So I have a question.
Dang it.
So the first part, why was it addition?
So really what's happening there is officially a Lewis acid-base reaction. We've seen that kind of activation step before. Say if I wanted to do a substitution for the bromine, I could have added HBr. And then run the substitution, right? So the substitution is still happening officially in the second step. We're running some kind of activation in the first part, okay? With HBr, it's obvious. That's an acid-base step. When we switch to now phosphorus tribromide, well, it's not really an acid-base step as we've defined it because acid-base is the transfer of a hydrogen. It's not a substitution because I don't have a leaving group. That's a lie. I do have a leaving group. I always forget to balance things. We do have that second piece. Okay? So we do actually run a substitution in that reaction. So that's nice. Right, does that make sense? So good catch on that. I was agreeing with addition. They look like two pieces to one. Okay? Does that make sense? Okay. This reagent, just like thionyl chloride, does work with carboxylic acids. NeOH will be converted across to the bromide, or the chloride if we did PCl3. Okay? Typically, we don't see PCl3 because what would we see instead? The thionyl chloride. We'd be doing a chloride substitution. Why not just use the thionyl chloride instead of the phosphorus trichloride? Okay? The tosylate. Okay? I don't want to go all the way back to it, but the TSCl/pyridine is what we had on that very first slide. We need to know what TS stands for. So TS is shown there with that little squiggly line. What does the squiggly line mean? What does that do?
There's more to it?
Yeah, there's more. There's something else out there. Whatever that something else may be. Okay? And I don't really care what it is, I just know that there's something else out there. So if that squiggly line is an OH, then we would predict that compound to act as what? Unfortunately, I got to plug in. So if you drew that out, and instead of the squiggly, you put an OH. What do you see? And now it's going to freak out on me.
Acid, right?
We had the OH there.
So it's an alcohol.
Why do you say an acid?
Because of electronegativity of the oxygen is pulling the electrons from the hydrogen, making the hydrogen acidic.
So you're saying that oxygen can pull electrons. But if I did ROH, this compound is not acidic. Alcohols are not acidic. Why are you saying the tosylate OH is? Let's make another kind of simplification. Does that look familiar to anybody? What is that?
Sulfuric acid.
Sulfuric acid. If I go through and now put the toluene aspect, that ring on there, does that change the OH the other end? Yes, but to a very small extent. Okay? It's still maintaining that same ultimate chemistry that we had in sulfuric acid. So the species will act as a Bronsted-Lowry acid, similar to sulfuric acid. What happens if instead of the squiggle or OH, I put in instead a chloride? Does that look kind of familiar? That looks an awful lot like so we could cheat and say SOCl2, also known as thionyl chloride, which we just saw. So if I make that a chloride, what happens to the species now? How does it end up acting? The sulfur now acts as an electrophile, similar to our thionyl chloride. That says chloride. So how does that work in our mechanism? Well, if the sulfur is acting as an electrophile, our lone pair electrons on our oxygen can come in and attack the sulfur, kicking out our chloride. And what do we end up with? Does the oxygen want to be positive? No, so what can it do?
Take the electrons from the hydrogen.
They can take the electrons from the hydrogen, and we'd end up with this structure. There is chloride still floating around, but the concentration of that chloride is relatively low. Okay? Which means we tend to not see the substitution outright with this. It tends to stall right there. What happened to the stereochemistry? And shaking your head isn't a bad answer. The stereochemistry is at what position? When do you have a stereocenter?
There's 4 bonds.
4 bonds. Does the oxygen have 4 bonds? No. Our stereochemistry would be centered at that carbon. Okay? If we had this as 1, 2, and 3. Did any chemistry happen at the carbon? So what happens to the stereochemistry at that position? Absolutely nothing. Okay? So if we go through to memorize the reagents and we look at that Tossel reaction and say, oh, well, that one didn't change the stereochemistry. Everybody goes, oh, well, it did retention. It didn't really do retention. It did nothing. In the other reactions, we had a retention because chemistry actually happened there. In this case, there's no chemistry happening at the carbon, so the stereochemistry isn't going to change. Okay? So think about where the chemistry is happening, not just blanket statement memorizing it changes or it doesn't. Does that make sense? What is now special about that structure that we have there? Said another way, if we looked at the tosylate's sister compound, what is special about that structure?
Has resonance.
It has resonance, meaning
Stable.
it is insanely stable, which means what can you tell me about it being connected to the carbon structure? The sister structure is not connected to a carbon structure. Once it has been removed, it is insanely stable. Meaning, while attached to the carbon structure, what do I have? Sort of unstable. I have a phenomenal leaving group. Okay? I've altered the alcohol chemistry to now not have all these other options, and now it really only has one option, to act as a leaving group and leave the structure. Because it is now large, what's going to happen? If it acts as a leaving group, where's our nucleophile going to come in and attack? It's going to have to come in from the backside because of that large leaving group. So thinking about the stability of each of those pieces and what happens if I break or make bonds is a really important aspect for scaffolding these reagents. Make sense? Okay. So what if we had internal ethers? Okay. Also known as an epoxide. So give me weird looks for internal ethers. Look at the structure at the end. Okay. What is an ether? It's an oxygen connected to 2 carbons. Right? So there's an ether. If I make it an internal ether now, those carbons are connected to each other. If it is a 3-membered ring for that internal ether, it's called an epoxide. If it happens to be more than a 3-membered ring, it's known as, I just learned this one like last year, an oxyrane. That's why you read the textbook. Right? So we get an oxyrane. The epoxide is the more important one to evaluate. Right? We've seen how to make an epoxide using MCPBA, so we should be okay with that. But we can also do it in another fashion. Okay? If we look again at our ether, or epoxide, we have those 2 reactive sigma bonds. Okay? How about I make one of them? Where would I expect those electrons to go? With the oxygen or with the carbon? With the oxygen. Which means if I took a step backwards, I'm probably looking, close enough, at something like this. Okay? As just a general concept. I can't have a formal positive, I can't have a formal negative. Okay? So how could I neutralize that positive while still keeping it positive but not add in any other chemistry? Add a leaving group. Okay, what leaving group do we want to add? Bromine's a great leaving group. Our halogens are phenomenal in that respect. Okay? I could get that negative oxygen, but again, I'm not allowed to have negative things as a synthesis. So what could I attach to that negative oxygen such that it's easily removable and still allows me that negative characteristic?
Hydrogen?
How about a hydrogen? Okay. And now I have a halogen and a water as part of my structure. I have what is known as a halohydrin. For everybody that had me first semester lab, that was the synthesis you did at the end of the semester, was a halohydrin. How do we get the halohydrin product? We do an addition. We do an addition with, cheat, it's on the screen. BR2. The BR2 would add 2 bromines across the structure. I don't want 2 bromines, I only want 1. Remember the first step of the addition is that or the 3-membered ring, cyclic intermediate. Okay. The bromonium ion, that bromonium ion structure breaks open when the second bromide as a nucleophile comes in and attacks. What other nucleophile could be present? First semester lab. H2O. By adding H2O, now when this reaction occurs, I get the OH up here. Do I have a stereocenter? Yes. How many stereocenters do I have? 2. So is it important to specify the stereochemistry? Yep. What is the stereochemistry? This is a review. That 3-membered bromonium ion, how do we break that ring structure open? Backside. It has to be a backside attack, which means one of them is wedged and the other one is dashed. How can I get that oxygen to be negative? Remove the hydrogen, which means that compound is acting as an acid. How can I remove the hydrogen? Add a base. The base removes the hydrogen. I would now have O minus. Now what can happen? Does the oxygen want to be charged? Nope. What can it do? It can share those electrons down and kick out the leaving group. And we'd end up with our epoxide. So it's an alternate synthesis to this. Okay? Let's throw in a quick test. What if somehow, okay, so let's ignore all this first part, so I don't care about all that right now. What if somehow you did your synthesis and you had the syn halohydrin, bromine dashed and the OH dashed? Could you still get the epoxide? All right, you had the strong base. What happens to the hydrogen? It disappears. We'd have the negative oxygen. Bromine's still a good leaving group, right? The oxygen could still attack the forming positive, right? Is that mechanistically allowed? No, good answer. Kind of the lead up into that, right? Why?
It's attacking from the same side that bromine is.
It's an orbital argument. The bromine is leaving on the same side that the nucleophile is attacking. That's not allowed to happen. It has to be a backside attack to allow this reaction to occur. We have to have one wedged and one dashed. This does not form the epoxide. Okay? It's a subtle change to the structure that all of a sudden shuts down the whole process. Make sense? Okay. So, epoxides. Side note, they're formed with alkenes, which means do I have stereocenters in the epoxide? Rhymes with fess.
Yes.
Yes. Yes, those are stereocenters. We need to specify those wedges. Okay. What is important? Actually, we don't need to specify them on that one because there's symmetry through that, so we don't need it. What is the potential issue with alkenes? Those could be stereocenters. If we put a methyl group out here, what does that then mean?
More than one product.
We get two products. As soon as you start with an alkene reaction, you will get two products. Okay? You have the top lobe and the bottom lobe of your pi system. Okay? So if we went through and did our epoxide reaction, we would get two products. That sucks. Okay? That ruins our yield. Until some nice guy by the last name of Sharpless comes along with a magic reagent known as Sharpless reagent. And the Sharpless reagent is a mixture as shown down below with plus DET or minus DET. The plus and the minus are referring to optical activity. Okay. By adding those things into the reaction, it forces one product over the other. Okay? It's known as chiral selectivity. Okay? Beyond that, that's all I want you to know. You can do that by adding this goofy reagent, and it works. I just thought it was neat. Done. Why do we care about epoxides? Take a look at the far right. All of those structures are natural epoxides. Okay? So this functional group does show up in nature, and they are all part to synthetically useful biomolecules. Okay, so we do care about epoxides. They may seem really weird and small and tiny and we shouldn't worry about them, but they are all useful. so we have to be aware of them. Okay? So what happens with the epoxide when it reacts? So number one, three-membered ring, right? Are three-membered rings particularly stable? No. So what happens? They break open. Okay? Do they break open evenly? No. It depends on the structure. So if we take a look at the structure drawn up at the upper right-hand corner, I've got two epoxides shown. All of those are different orientations of the same epoxide. Okay? I would argue the one on the left is easier to see. Okay? What we're saying is the epoxide ring is in the plane of the paper, and then the R group is coming at you, the hydrogen is going away. Stop playing with your phone. The other version is the epoxide is coming out of the paper at you, and we have the carbon structure in the back or in the plane of the paper, and then the hydrogen going away. Not the easiest matchup to go through and see, but that's what's happening. If I now run under basic or neutral conditions, okay, what that means, I can't walk, is that I'm adding, because I'm tied, I have a negative nucleophile. A negative nucleophile would be what? Give me a descriptor, a one-word descriptor.
It's strong.
Strong. If it is a strong nucleophile, that suggests what type of mechanism?
SN2.
SN2, which would suggest backside attack. Okay? So if we look at our epoxide, I could do a backside attack, or I could do a backside attack. So cool, we know it's SN2, but we just stuck ourselves with two possible backside attacks. Is one of those better than the other? Yes. Why? We have 1 versus 2.
2 is better.
2 is better. Why? It is easier access. Why do I care about easier access? Okay, we'd get electron-electron repulsion. Why do I care about electron-electron repulsion? What doesn't want to happen as easily? What mechanism? It's an SN2 mechanism with backside attack. Because of that, I want the least sterically hindered attack. The nucleophile will come in at the 2 position, not the 1. That will force open our ring structure, followed by a protonation. So I didn't do a good job on that. I always screw that up. We do step 1, our nucleophile, followed by step 2, the addition of acid to protonate the alcohol. And we would end up with the product shown. Again, nucleophile versus the OH, are they on the same side or opposite sides? It's drawn on there. They're opposites because we are doing a backside attack. Notice where the nucleophile is located. It's located on the least sterically hindered side of the epoxide. The alcohol is on the most substituted side. Okay? And all of this has to do with the epoxide not really being ready to break open. Okay? So the nucleophile being strong dictated the chemistry. When do we have a strong nucleophile? When there's a negative. How do we get a negative in solution? In a basic environment. I will never have a strong nucleophile in an acidic environment, because an acidic environment provides H+. The H+ would cancel the negative nucleophile. Okay, so we have to be in a neutral or basic system. But what happens if we move to acidic conditions? Mother. Well, under acidic conditions, now what's the most reactive thing? The hydrogen. Okay, I have a positive hydrogen. Let's neutralize that positive hydrogen by doing what? The electrons from our oxygen need to come in and share. The result being, I would now have a... don't look at the answers. I would now have a positive hydrogen, or positive oxygen. Okay? The nucleophile is not strong. How do you know the nucleophile is not strong? It's not charged. Okay? So the most reactive thing that I now have to focus on is actually on that oxygen. I'm concerned that that oxygen is positive, which means it's going to start to fall apart. How is it going to fall apart?
Open the ring.
We'll open the ring. How? There are two bonds with which it could open.
Well, it would be it would open on the more substituted carbon.
Why does it break the red bond and not the purple bond?
Because on the red, it can stabilize the charge better. The positive
Okay.
charge.
That oxygen is effectively already leaving. So this is not a formal structure down here. This is just an idea of what's happening. That oxygen is already on the way out, which means I'm starting to form a carbocation. Where is that carbocation more stable?
Secondary.
On the secondary, the more substituted side, which means the epoxide will now fall apart so that the nucleophile attacks which position?
More substituted.
The more substituted position. The result being that I get the nucleophile at the other position. That is significantly different than under basic conditions. Under basic conditions, I got the opposite substitution pattern. Everybody see that? Okay. This is not some weird exception thing with epoxides. They just do crazy, weird things in different locations. Change the conditions, you change the active species. The active species is what you need to address and neutralize first. Under basic conditions, it's that nucleophile. You need to stabilize the nucleophile as quickly and as efficiently as possible. Okay? Under acidic conditions, it's the acid. You neutralize the acid first by protonating the epoxide. Now you have a new unstable species that you have to stabilize. Okay? That structure will fall apart in such a way to make the most stable products. Okay? The nucleophile won't come in and attack the most or the least substituted position because the oxygen doesn't want to break that bond. It's already breaking the other one. There's not a strong nucleophile here, so we end up attacking the more substituted position in an SN1-like fashion. I have to call it SN1-like because the nucleophile is still attacking from where? The backside. Right? So the epoxides are still doing kind of an intramolecular-ish substitution reaction. We never have the leaving group leave the structure. It just leaves the carbon where the chemistry is occurring. Right? So it's just a question of where you're attacking and why you end up with those positions. Kind of makes sense? If it doesn't make sense, your other trick, memorize. Okay, so we get our substitution at the other site. Our epoxide summary, MCPBA or other peroxy acids tend to be the big one. Okay? Or you could go through the halohydrin intermediate. Your reactions of the basic or neutral conditions, you get those products. Your acidic conditions, you get those. So it's just a summary slide, okay, of the previous ones. So if we took a look at this one, what do we get for the product? So what are we starting with? We have an alkene. Pi bond's reactive. Pi bond's reactive is what? A nucleophile. So when we look at our reagents, what are we looking for? An electrophile. Okay. Where's our electrophile? Water or chlorine? Why the chlorine? Doesn't chlorine have a ton of electrons? It's Cl2. We can get a polarization in that structure. We can form that cyclic chloronium ion. Yes, that is a valid word. Okay, we should be showing the stereochemistry. Okay. That would be our intermediate. What's the nucleophile to break open that very unstable charged intermediate? I don't accept hydroxide. water from H2O. Okay. If water was not present, what would be our nucleophile? The chloride. The result being from that very first step, what we end up with as our first product. Whoops. Where does the water attack? More or less substituted position. Is it a strong nucleophile or a weak nucleophile? It's a weak nucleophile. Is it a good leaving group or a bad leaving group? It's a good leaving group. Good leaving group, weak nucleophile, which type of mechanism? SN1, which means our nucleophile should attack the more substituted position. It is still unfortunately going to do a backside attack. So there's our OH, there's our chloride. Right? Because it's a backside attack, that methyl group gets pushed from the front to the back. Now we add NaOH. NaOH is a strong base. What do we need to find? An acid. Where's there an acidic hydrogen? On the oxygen. So the end of step 2, what do we have? Could go through and say we got this, right? That negative oxygen is what? Strong nucleophile. Chlorine is a good leaving group. We get the intramolecular reaction. We actually don't stop at that negative charge. What do we have? We have the epoxide. We then follow that up with methanol and TSOH. TS. What was that? That was that tosylate. When we said it was OH attached to it, the tosylate acted as an acid. We've got a strong acid. TSOH is effectively H2SO4. What's the most reactive thing? Our H2SO4 protonates. Now what happens? We have a great leaving group. I need to find a nucleophile. Where's my nucleophile? I don't accept. CH3OH. The oxygen will come in and attack which position? The more or the less substituted? The more substituted because good leaving group with it already being charged. It starts to bust open right away. Okay. The result, the stereochemistry at that position does not change because no chemistry happened at that carbon. What's the stereochemistry at the other position? What do I have? Where did the methanol come in and attack? Backside, which means it must be dashed because our epoxide was wedged. I'll add that hydrogen temporarily, which means the methyl. Oxygen doesn't want to be positive. What happens? Gives up the hydrogen to solution, and we have our final product. That's our synthesis. Are you responsible for all of that? Yep. Every single one of those steps are things that we have already talked about this semester. Okay? You are responsible for stringing these together. Do not look at a question and be like, well, crap, I don't know what the final answer is. I do not expect you to know what the final answer is. In fact, I looked at this and had no clue what it was. I shouldn't admit that, but that's true. Okay? I didn't. look at each reagent step, draw out each of those products, decide what you end each step with, then move forward, then move forward, then move forward. By practicing these is when you'll be able to get through it quicker and faster. Does that make sense? Oh, I don't know why I walk. My back is killing me. Nitrogen, okay, or amines in substitution and elimination. So we had oxygen attached to our structure. What happens if we put a nitrogen on there? What chemistry do we have available to our amine? Good. The lone pair on the nitrogen. I agree. The lone pair is sweet and amazing. That lone pair will make the nitrogen act as exactly a base or a nucleophile. Okay. I have hydrogens attached to that nitrogen. Nitrogen being more electronegative could theoretically take the electrons from the hydrogen. Unfortunately, nitrogen's electronegativity is not enough to pull the electron density away from the hydrogen, meaning the hydrogen has no chemistry. It is not acidic. Right? For that same reason, the carbon is also not particularly electrophilic. Right? But if I can tweak the nitrogen, if I can change it to be a better leaving group, I can make that carbon electrophilic. Does that make sense? So what we're doing is we look at our structure, evaluate the chemistry, and try to enhance or move it forward. Yes? It's leaving group means it takes the electrons.
Oh.
So that's why it's not a good leaving group. What I was talking about is it acting as an acid, nitrogen taking the electrons from the hydrogen. Okay, and we'd have H+. Nitrogen is not electronegative enough to withdraw the electrons away to make that hydrogen positive. Okay, so when you look at the periodic table, fluorine, chlorine, bromine, iodine, all pretty good at pulling the electrons away from the hydrogen. So most of or all of those are acids. We move to the next column over. HO, HS, HSE, all of that fun stuff. Those have kind of an intermediate chemistry. Oxygen can act as both a base and as an acid. It's not a strong acid, but it can do it. Okay? Nitrogen has even lower electronegativity. It doesn't have enough characteristics to remove the electrons. It can't act as an acid. It does still have the electrons, which means it could act as a base. So that's the big chemistry for nitrogen, is it can act as a base and a nucleophile. And that's pretty much it when we look at the amine functionality. Okay? So for reactions to enhance or stifle the chemistry, I could try and enhance the chemistry of that carbon, making it more electrophilic, if I could make the nitrogen not have electrons. Right? Which means I need the nitrogen to ditch those electrons to another atom, making the nitrogen positive. If it becomes positive, I can make that carbon willing to accept electrons because now the nitrogen could act as a leaving group. Okay? If I wanted to stifle the chemistry, that becomes a little bit trickier. It's all still centered on that nitrogen. What can I do? What am I trying to do with it? Okay? So first thing we could do is look at substitution. So if I start with an alkyl halide and ammonia, okay, I can have the nitrogen attack the carbon as shown, right? It's a nucleophile, electrophile with the alkyl halide. I can have another ammonia remove a hydrogen, and I've now done a substitution for that bromide. Everybody agree with that mechanistic step? Nothing on that, and you're like, oh, that's too weird, don't do that. Okay. What is an interesting property of that primary amine?
That's lone pairs.
It has lone pairs. What did the starting amine have?
Lone pairs.
Lone pairs. Did I get rid of the lone pair chemistry? No. So guess what that primary amine now does? It can react with alkyl halide that's still in solution. So I could do this substitution once, or I could do it twice, or I could do it 3 times, or I could do it 4 times. It stops at the fourth because there's no more lone pairs. So nitrogen is particularly irritating and frustrating for this because it has lone pairs all the way through, and it can offload those hydrogens relatively quickly once it's accepted that fourth bond. So it can shuttle that hydrogen off and now have lone pairs again and now initiate the whole cascade again. This is why nitrogen sucks for substitution reactions. Because if I try to do a substitution, I don't get one product, I get four. Okay? That really messes with the yield. Okay? So for straight substitution, nitrogen is awful. We don't use it. Okay? What happens? How could I force just one product? Let's try that question. I want one product. Have I specified which one product I want? No. So how about you pick a product and tell me how I make that one product? Yep. There's a way that we can do this substitution reaction and guarantee only one product and not four and get an awesome yield. You want a hint? I'll give you the product.
You do NH3 in excess? Or just keep it?
NH3 in excess? If you do NH3 in excess, you now have tons of ammonia. That's going to react out the halide. You aren't going to end up with just the quaternary. But what if you flip it on its head, and instead of doing the NH3, you do the ethyl bromide? You do the bromide in excess. Now what happens? Well, if there's tons of bromide, if it sees the primary amine, what's it do? Substitution to make the secondary. There's still tons of bromide. I have the secondary, it still has electrons. Reacts again to form the tertiary. So if I add in excess of the alkyl halide, I can force the quaternary. But that's the only one I can force. Okay? I cannot get the primary, secondary, or tertiary in any reasonable yield. I can really only force the quaternary. Okay? So what can I then do with that? Okay? Well, if I go through and do this, and now do a simple change. I added the excess, and now I add sodium hydroxide and heat. Heat is a signal for elimination. Sodium hydroxide is a strong base, which is a signal for elimination. So I'm adding, still methyl bromide, but now I'm adding two Qs to do an elimination reaction. In the elimination, what should I make? A pi bond. Okay? My leaving group is going to have to be centered on that nitrogen. That has to be my leaving group. Where should I form the pi bond? Red or purple? Internal or external? Shh. And potentially shh to you too, but you for sure need a shh. Red or purple pi bond? Elimination reaction, what do you expect? Why purple? It's not a secondary carbon, it's that the pi bond would be more substituted and thereby a more stable product if I formed the internal pi bond as opposed to the external. Yet what happens? We get the external. This is chemistry flipping on its head. It shouldn't be doing this by all rights and purposes, which means we attach someone's name to it, the name we attach, the Hofmann elimination. Okay? The how and why behind this is in the next sequence of slides, which your textbook does a really good job, so I pretty much stole their pictures. Okay? It comes back to Newman projections. So if you want to go back and look at that in more detail, you can. Ultimately, what you need to know is your amines are only useful for elimination reactions, and the elimination product you form is the less expected one, the less thermodynamically stable. That's what you need to know from the amines. That's it. With that, we are done, a little bit late. I did not talk at all about the reactivity of the CH functional group, in particular, its proximity to a carbonyl. So do not worry about enols or enolates to the level of detail that your textbook or your online homework talks about it for the exam. Okay? That will get pushed into the next exam. So we're really up to the Hoffman elimination. You can fully expect some enols and enolates to show up for two reasons. One, we saw it already with our alkynes. Two, the chemistry that they're addressing in the textbook at this chapter is actually old chemistry. It's acid-base chemistry. You know how to do that. Okay? So I will push you on those questions and put them into the exam, just not to the super level of detail that the textbook goes into. We'll pick up with that after the exam. I will post a video about kinetic and thermodynamic that I expect you to watch before the next lecture meeting. Not the next exam, not the next period, because next period is the exam, but the next lecture meeting. Okay? And I think it's actually relatively short.